a lot. First of all, I would like to thank the scientific committee for the invitation. It's a great honor to contribute to this conference. And of course, I would like also to thank the organizing committee for this amazing organization. It is so impressive. I think we all share this impression. Anyway, so I'm going to speak about optimal immersions. So immersions, which are critical points of some classical Lagrangians. In his talk, Jinsu on Wednesday insisted on, the applications in geometry of the study of these special immersions. So in intrinsic geometry and also in extrinsic geometry. Me, I'm more an analyst, so I'm more interested in, you see, the impact of the study of these immersions on analysis and the way, you see, the conjectures, which are, classical conjectures in this geometry, are stimulating the development of analysis tools. Okay, so let me go to this notion of optimal immersion. So you have here a surface, will be a closed surface, so without boundary, oriented for the rest of the talk. And you are looking at mappings into arbitrary Riemannian manifolds here, which are immersions, that is, the gradient has full rank everywhere. And so it is optimal when, for instance, it is a critical point of the area. It was discovered in the 18th century that the first derivative of the area is the mean curvature vector. Or it could be also optimal with respect to the so-called Willmore energy. So here I'm restricting to immersions into the three sphere, but you can also define the Willmore energy in a much more general context, and in particular in this very general context. Here you have the two principal curvatures, so this is my normalization. This energy was introduced in the early 19th century in an effort to extend the theory of elastica of Bernoulli and Euler to two-dimensional membranes. And this was first introduced by Sophie Germain, and the Euler-Lagrange equation was derived by Siméon Poisson at the time. That was a tour de force because Lagrange was still alive and deriving the Euler-Lagrange equation using the variations method introduced by Lagrange was extremely innovative at the time for this kind of functional, which is giving a fourth order elliptic PD, very nonlinear one. Or it could be also a critical point of this functional, and I will come back to that. I will come to that at some point. So this functional, no worry if you don't get it at once, is the area of the Gauss map. So the Gauss map, for map into S3, you see, you have the three sphere here. You have your surface in the three sphere, and you have the unit normal, n, and you are producing phi wedge n. And you're looking at the area of this object, which is a two vector. And you can prove that this is given in terms of the principal curvature by this expression. So we'll see that. So now let me see our first optimal surface. This is the following one. So we take first the Willmore energy. So this was a result which takes its origins in the first result by Chern and Lashoff. It was for a different Lagrangian for the total curvature, but I think it was a source of inspiration by Willmore himself, who proved the following inequality. So the Willmore energy that I gave you is always larger or equal to 4 pi, and equality happens if and only if the surface is a geodesic two-sphere, so really the S2, the intersection of an hyperplane passing through the origin with the three-sphere, or a Möbius transformation of it, because this energy has a very special features that it is invariant under conformal transformation. And this is the only energy, by the way, depending on the second fundamental form, which has this property modulo some null Lagrangian, that is modulo the addition of the integral of the curvature, the Gauss curvature. Okay, so how should we think about this lower bound? I think a right way to look at it is the following, is the Fenchel theorem. So I give you a curve, you see, and I'm assuming the curve is closed. This is exactly like in the previous slides. The surface was assumed to be closed, you see. So if you make this effort to close up the curve, then you see there is a famous theorem by Fenchel, which is telling you that the integral of the curvature is larger or equal than 2 pi, and equality holds if and only if the curve is planar and convex. So this is a bit the way to think about the previous lower bound. So the previous lower bound on the Willmore energy, by the way, has applications in general relativity while considering the Hawking mass. It is measuring how far you are from a very flat situation. Now, let's go a bit, let's play a bit with this energy, and let's assume that you know, we have some more complex embedding of our curve here. And this is following result by Fari and Milnor. It says that if the curve is knotted, that is, it's not isotopic to this planar curve for which we had 2 pi, you see, then the lower bound is multiplied by 2. It's 4 pi. So in this situation, for instance, you must have 4 pi. So this is one direction you can go. You can assume something on the style of the way you are immersed. And, you know, there are many lower bounds nowadays. I'm just going to mention one more, or two more, in fact. Now for surfaces. So now if you assume, going back to surfaces, if you assume that your surface has a point of self-intersection. So this is a famous result by Peter Lee and Xingtung Yao in Invenciones in 1982. So you take the immersion of a closed surface here in S3, and you assume that there is a point with n pre-image through this immersion. Okay, so there is a self-intersection n times at a given point. Then what Lee and Yao proved is that the lower bound is increased. It is 4 pi times n. Okay, so for instance, you can deduce that if the Willmore energy, which is here, is strictly less than 8 pi, the immersion has no self-intersection. So this is an embedding. And for instance, here in this situation, it's automatic that the energy is larger than 8 pi. So this energy is measuring something about, you know, the way you are immersed. But even more, in fact, you could also make topological assumptions which are not about the way you are immersed, but which are about the surface itself. And this is the famous Willmore conjecture in S3. I'm formulating it in S3, and which was proved by Marquez and Neves in 2012, but published in 2014. And it says the following. Assume your surface is not a sphere. You see, so it's a closed surface oriented, and the genus of the surface is non-zero. Then, you see, that was a conjecture formulated by Willmore in his 1965 paper. He was proving it for axially symmetric tori in R3, and he was making this conjecture that there should be this lower bound, which is 2 pi squared. And this lower bound is nothing but the Willmore energy of a famous torus, which is so-called Clifford torus in S3, which is simply, you take S1 times S1 divided by square root of 2. And so this is what Marquez and Neves proved. And we are going through their arguments and try to draw some lessons from their approach. And yeah, so let's go a bit into that. So first of all, just to have an idea how this torus looks like. So if you stereographically project it, you get it simply by, you know, you take this vertical circle, which is centered at the point of coordinate square root of 2, 0, 0, and which has radius 1, and you rotate it along the z-axis, and you generate an axially symmetric torus, and this is a stereographic projection of the previous torus, which was of the torus, the Clifford torus. Okay, so now what was the idea of Marquez and Neves? In fact, there were partial results by Peter Lee and Xingtung Yao also on, some cases for some conformal class, you can prove the Willmore conjecture by direct minimization using the notion of conformal volume. But what Marquez and Neves conceived is that instead of doing a minimization, you are going to work with less coercive energy. So you are going to exchange a minimization procedure of a slightly more complicated energy with a min-max operation of a less coercive energy. So you have here, you have a minimizer, but instead of minimizing for integral of 1 plus h squared, you are going to do some kind of min-max for the area. So what is the relation between the two? The area is just the integral of 1 with respect to your volume. So you have obviously this inequality, and equality holds if and only if your surface is minimal. Okay, so this looks a bit, you lose somehow, because we all know that minimization operation, absolute minimization operation, in a sense, is easier. Well, it's not convex, but still, a priori, it's an easier variational operation. So you give up the minimization because the Lagrangian is slightly complicated, and you go for a simpler Lagrangian, but there it is dominated by the previous one, and we will see it might have negative directions and so on, so you will do some min-max. So this is the strategy they're adopting. So in fact, Marquez and Neves, one of the main results of their paper is about minimal surfaces and not about Willmore. I mean, it is about Willmore. So what they prove is that the minimal surface of lowest area in S3, which is not a geodesic sphere, as I was describing, this intersection of an hyperplane going through the origin with S3, are rotations of the Clifford torus. So let's go a bit in their proof to understand how you can exchange minimization into min-max. So it is so that there are some negative directions for minimal surfaces there. So there are two styles of negative directions. So if you take a minimal surface, which is not a geodesic sphere, it has at least 5 negative eigenvalues, including the multiplicity. The first one are coming from the action of the Möbius group. You see, this one was invariant under the Möbius group. This energy is less coercive. Therefore, it is sensitive to the Möbius group. And as soon as the Möbius group acts on your surface, it is decreasing the energy. So this is the first possibility. So this is here the kind of transformations you could apply to your surface. Of course, modulo isometry. These ones are producing really strictly negative eigenvalues. And you can also do a parallel displacement of the surface along its normal with constant speed. So what does it mean? It means simply that you are considering this transformation, where n is again our normal. You are considering cos t times phi plus sin t times n. Now, you might ask yourself, so this is always the case, you always have these negative directions. So is there any surface which has only these negative directions? So for the two spheres, for the geodesic two spheres, these directions, more or less, they are collapsing because it's very degenerate, so you don't have the same order of multiplicity. This is why I was excluding the geodesic sphere, and by applying this, it corresponds to apply that, so it's a bit degenerate. But you wonder whether there is a minimal surface which has only these negative directions. And this is a theorem. Yeah. So I was 2 weeks ago in Granada, and his students, of course, Francisco Urbano, that was his birthday, has many, many results. But I think there is one that captured the attention of his students, which is written here. I'm going to put it on the slide. It's relatively short. You can put it on a cake. So this is an artistic representation of the Clifford torus. And maybe, yes, there's more. Yeah. So this is the result. So every closed orientable embedded minimal surface in S3 with index less or equal than 5 is either the sphere or the Clifford torus, the previous torus. Okay? So if you restrict to that, you have only this one. So in that sense, you see, for not anymore for the Willmore energy, but for the area, the Clifford torus is optimal because it is a surface which has exactly these negative directions. So now how do you prove the Willmore conjecture? So in a nutshell, so first of all, you introduce a min-max problem on the area for surfaces with genus strictly larger than 0. And here you see surfaces is very vague. In fact, it has been mentioned in several talks since the beginning of the week that you see the min-max operations for surfaces has been developed by Almgren and Pitts using the formulation of varifold. So here we are speaking about so integral varifolds, so rectifiable ones, but we are speaking about very, very weak notions of surfaces. And what they proved is that there is a min-max operation. So here I'm not going to go into the details. Here you have calligraphic A has to do with all admissible families. So you have to imagine when you think about the mountain path, for instance, you see, you are looking at all possible paths joining 2 points. It's a bit like this, except that it's 5-dimensional paths, you see. It's not only 1-dimensional. And you look at all possible paths with some boundary conditions. I'm not going into that. And you look at the optimal way to realize this. So you look always at the saddle point, you see, the maximum, and you minimize it. And what they proved is that they proved that it is realized, what is called the width, you see, by reference to sweep outs of bodies. When you do some kind, it corresponds to a min-max. When you do that, if the width, so the width is realized by the area of some minimal surface of index less or equal than 5. So you have to imagine that here it's a bit outrageous to write their proof in this way, because behind this, first of all, there is a strict inequality. There is a realization by a nice minimal surface of index less than 5. So you have 100 pages which are itself based on the Pitts and Pitts theory of several hundred pages. So yeah, so but let's take it this way. And now, if you use Urbano's result, you know that it cannot be a single geodesic sphere because the width is strictly larger than 4 pi. And it cannot be 2 copies of the sphere because of, by testing, you know that this width is strictly less than 8 pi. Okay? So it has to be then automatically, thanks to Urbano's result, it has to be the Clifford torus. No. Once you know that, comes another ingredient, which was originally introduced by Antonio Ross, and which was refined and reworked in a very clever way by Marquez and Neves. We have seen that infinitesimally, you have 5 directions which are negative. So you have the Möbius group action, and you have the pushing of your surface along its normal. So this is infinitesimal. So here, what Ross is doing is that he's making it global. That is, he's just considering all Möbius transformations of your surface, as well as all, pushes of your surface. And this is creating what he called a canonical family, and which has to be refined also in order to guarantee the strict inequality at the boundaries. So I'm not going into that. A bit technical, but this is where there is the beauty of the result, in fact. And I feel a bit embarrassed to hide that at this stage, but maybe I'll come back to that later. And what you prove is that for any embedding, you see, you can produce such a path, 5-dimensional ones, so such an admissible family, which is controlled by the Willmore energy. So this is where, so therefore, you see, the width is always less than any, by the Willmore energy of any surface, any immersion, any embedding, say, of, and any immersion also, of surfaces of non-zero genus. So this special family is called the canonical family of phi. Okay, so let me give you, in order to illustrate a bit this min-max operation that I was hiding in this line, let me give you an explicit one, which is some kind of cousin problem to the Willmore problem. It's a problem that I posed in 1996, and I was considering the 3 energy of maps from S3 into S2. Okay, so you go from S3 into S2, and you want to minimize the 3 energy among maps which are non-homotopic to a constant. So the 3 energy itself is again invariant by conformal transformation. So if you compose with a Möbius group, the 3 energy remains unchanged. So the Hopf vibration is supposed to be, in my paper, I was posing the question whether the Hopf vibration, so this is extracted from the book of Penrose, is a minimizer of the 3 energy. So here you have the explicit formulation of the, so this is a projection. So in the domain, you do stereographic projection, so you see it as a map from R3 into S2. And these tori, they are just pre-image of horizontal circles in S2. The lines are pre-image of points. They are linked and so on and so forth. So it's a very beautiful object. And so this is a claim. So, and again, you can adopt the strategy of Marquez and Neves. You can say, let's convert the minimization of a complicated energy, because people in the audience used to calculus variations, they know that the P energy is not that easy to handle. And we much prefer the Dirichlet energy, which is quadratic, which is, you see, which is much more beautiful. And instead of minimizing the 3 energy, you look at optimal saddle points of the Dirichlet energy. What is the relation between the two, which corresponds to this inequality? This is the following inequality, which is just Hölder inequality. Okay? So we have here an energy which is conformally invariant, the 3 energy, which is there, and below we have the 2 energy, and equality holds in particular for the Hopf vibration. The Hopf vibration is megasymmetric. It has a gradient which is constant everywhere. So there is a fact which is also very reminiscent to what has been proved for minimal surfaces. This was discovered by Hamed El-Soufi. Every non-constant smooth harmonic map from S3 into S2 has at least 4 negative eigenvalues. And these 4 negative eigenvalues are just coming from this Möbius transformation. So if you apply, and now, you see, you can see that in fact, if U is harmonic, if you compose with all Möbius transformations, so it's a smooth harmonic map from S3 into S2. Yes? You take the second derivative of the Dirichlet energy. Okay? So, and you see, because we had exactly this situation with the 3 energy was here. Now you look at the pushes by the Möbius transformation. The 3 energy doesn't see it. You stay at this energy level. While for the 2 energy, which is less coercive, which is below, immediately, poof, you lose energy. So you have negative directions. And this is again reminiscent to what you had for minimal surfaces. And now you wonder, it's very natural, is there an harmonic map which has exactly these negative directions? You see? In fact, so this is what I proved in, so it has been published last year. If you take a smooth non-constant harmonic map of Morse index less or equal than 4, then this is an harmonic morphism. That is, more precisely, there is a rotation in 4 space, an holomorphic diffeomorphism of CP1, and the map is a composition of this rotation, the Hopf vibration, and this holomorphic diffeomorphism. So, in a sense, this corresponds to Urbano's result. Okay? So now we can imagine the same strategy as Marquez and Neves. So let's produce a min-max adapted to this information. So which min-max do I propose? I propose the following min-max. I am considering, so now I'm making very concrete, now I'm making it very explicit to everyone. This is here. You take continuous map for the W12 topology from the closed 4-dimensional ball into W12, S3 into S2. And what you require is that when you go at the boundary, when you you look at the boundary of before, your map is constant. And when you collect all these constant, it's a constant map into S3. When you collect all these constant maps, you realize a map which has an Hopf degree which is homotopically non-trivial. So this is the power. This is a power set of the space, of maps in W12, S3, and S2, and you are going to perform a min-max on that. So you are looking at. You take the Dirichlet energy and you take the min-max on this. Okay, and what you can prove is that first of all, this class is non-trivial. It's super easy. You just take a map which has Hopf degree non-zero, and you just compose it with a Möbius group. That's it. Okay, so this is non-trivial. And then using Poincaré inequality, you prove that the width is strictly positive. And you wonder, what is the value of this width? So I was conjecturing that this is the Dirichlet energy of the Hopf map. And in fact, if we can prove the width is achieved by a smooth harmonic map using of index less or equal than 4, using the previous slide, you can conclude that this is the case. Okay? So all the question is an analysis question, is a realization of this width. So, and this would imply the conjecture, the mapping Willmore conjecture, because then, you see, the 3 energy is controlling the width with the 2/3 here, and with this multiplicator coefficient, if U is non-constant. And if the width would be equal to the Dirichlet energy of the Hopf map, then you have this inequality, which implies a conjecture. Because, again, for the Hopf map, you have an equality here. Exactly like for minimal surfaces, you have equality between the two. Okay, so I just wanted to illustrate this min-max operation, which was more intricate to describe for Willmore. I did some digression into harmonic maps. Now, let me do some, some listing of some dictionary of the two problems to have some kind of comparison. So you have the Willmore energy, which is conformally invariant. You have the 3 energy. You have the area. You have the Dirichlet energy. You have the canonical 5-dimensional family of Marquez and Neves. You have simply the 4-dimensional Möbius group action. You had the bounds by Antonio Ross, that is, so, and you can use Ahmed El-Soufi bound here. And Urbano's result, and the result, in fact, it was a result in 2019, but it was published last year. Anyway, so this is a picture, but this is not what is interesting me. What is interesting me is the analysis. So how do you implement, what are the available analytical tools to implement min-max? So here, I mentioned briefly that the implementation by Marquez and Neves requires the use of Almgren-Pitts theory and this notion of almost minimizing varifolds. which are very singular objects. And you can understand that in a sense, it is intrinsic. They could not use, because I spoke with André, and he was telling me at the beginning we tried some things to work on a smoother class. But in fact, it's intrinsic. Why? Because the fifth direction, the direction which consists in pushing the surface along its normal, is going to produce very nasty objects. And this is why you have to, if you look at the admissible families, you have to include very singular surfaces. So in a sense, using Almgren pits is extremely natural in that. But still, you have to remember Almgren pits is codimension 1, and I will come back to that. And this is something I would like to avoid. So here, you use harmonic map theory. There is some ongoing work with Daniel Stern, who is speaking in the other building. And so we are kind of making progress in this direction. It's more harmonic map theory. Okay, so I would like to mention some min-max theory that I developed in collaboration with my former student Alessandro Pigatti in the last years, which unfortunately cannot be applied to the Willmore conjecture as it is right now. So you take the space of immersions of a closed surface, a closed two-manifold here. You can take also the union of this for several sigma 2, for a finite number of sigma 2 with a bounded Betti number. And then you take, so I'm not going into this, but an admissible n homological family of M. That is, you take a subset of the power set, which is invariant under homeomorphism of this set here. And it is n-dimensional. So it could be n homotopical family or n cohomological family as well. So n has to do with, you know, the one dimension when I was speaking about Montaigne Pass, the 5 dimension when I was speaking about Marquez-Neves proof, or the 4 dimension for the harmonic map situation. And then what you prove is that if you have a width which is strictly positive, then it is realized by a smooth branch immersion for which you control the genus here. And I think the most important information is the last one. You control the index. That is, in fact, you have a multiplicity 1 situation. You don't have, you see, you don't have a situation where a surface is equipped with a multiplicity 2, and there it's difficult to define the index because you don't know if you can decouple the two multiplicity into 2 objects. You see, well, we have here exactly multiplicity 1. So that was really the main issue in this paper in Duke, was to prove that the index is controlled by n, that we have multiplicity 1. Anyway, so I was just mentioning this because just to show that this is completely inadapted to Willmore. You cannot use that for Willmore because you're working on immersions, and again, this 5th direction is bringing you to spaces of objects which are singular. But still, we will see how to bypass that. So yesterday, Leon Simon was making, was a statement about the embarrassment of the community in terms of, how stuck the community is for proving improvement of regularity since the work of Allard for general stationary integral varifolds. And I share completely this embarrassment. And now what is behind the result is a new notion we have, which comes naturally from the variational problems we are considering, the notion of parametrized stationary varifold. Maybe I should take a few minutes to explain what I mean by this. With parametrized stationary varifold, you have an integral varifold, but the integral varifold is equipped with a parametrization. So you have like a surface here, and it has, so it is given by a map, you see, and there is also an integer multiplicity coming. And so you have a surface, a map, an integer multiplicity. This map is continuous and weakly conformal. You can take it. It's a smooth surface. And now you have the following localization property. If you take any function, which is C2, and you look at the upper level set of this function, so for almost every upper level set, you see, you look at f equal t, and this is the image of f equal t. And then the parameterized varifold is telling you that you are stationary. The parameterized stationary varifold is telling you that if you take any perturbation in the target, in the ambient space, which is avoiding the image of the level set, of this part of the level set, so here you are somewhere here. If you take any perturbation which is avoiding this boundary, okay, so if you take x such that the support of x is in your space, what was the space, whatever, mm minus the image by phi of f equal t, then you are stationary. You have the stationary condition satisfied here. And this localization property is very, very powerful. Let me give you one example, even in 1D. So I'll give you a classical example of a stationary varifold which is singular, which is, okay, so this is supposed to be S2. You take half geodesic, so you take a meridian, you take another one with an angle 120 degrees, and a third one behind with also, again, 120 degrees. And you put multiplicity 2 on them, okay? So this happens to be a stationary varifold, one-dimensional stationary varifold in S2. The thing is, it is not, you can parameterize it, so you can find, so this is now the circle, which is, you can find a map which is going, you know, when you go along the circle, you are going to go along your varifold, so it is parameterized. But it does not have this localization property. Why? Because if you just start from here and you go once there and once here, you just end up with 2 meridians, and this is not stationary relative to its boundary. So this is not, so it is parameterized, but it is not parameterized stationary in the sense which is here. And this is why, if you read, for instance, the works of Neshan Vikramasekera, is facing this situation like this triple junction, and with the parameterized things, we avoid them automatically by the structure. And they come naturally from the variational problem. Okay, so anyway, so we cannot use it for Willmore. And just to insist on that, so if you follow the Ross-Marquez-Neves canonical family, you end up by, you know, looking at wavefront evolutions. Even if you start with an analytic surface, you can produce, so these two first kind of singularities, which have been classified by Arnold, are generic. The other ones, they are generic in evolution, which is exactly what we have in the fifth direction. So therefore, the previous 2 slides with Alessandro Pighetti is really collapsing with this reality. We cannot do anything. So conclusion so far, checking the time. I don't know, do you have the time? 20 minutes, okay. Conclusion so far. So we aim at considering the optimality of the Clifford torus in arbitrary codimension using minmax theory. The Almgren-Pitts minmax theory is codimension 1. This we know, to know. Huh? And that is the regularity of almost minimizing integral varifold is known in codimension 1 so far. The canonical family, as we just saw in the previous slides, is intrinsically singular due to the fifth direction. And this is really intrinsic. Because minimal surfaces, they are sensitive to this fifth direction. They have to go through this fifth direction and create these nasty cusps. So, and it is forcing us to very weak notions of surfaces. So, is it possible, at least, not even speaking about higher codimension, is it possible to come back to Willmore in 3D and make a different proof. So this is the subject of my talk today, is to propose a different proof. So I first propose a desingularization of the canonical family. So how do you do that? That is, you have immersions from sigma 2 into S3, and you look at the Gauss unit vector. That is the vector which is in S3, which is tangent to the surface S3, and which is orthogonal to your immersion. And now you can produce, using these two vectors, you can produce the two-plane generated by these two vectors in R4. So the space of two-plane here, G2R4, is identifies to CP1 times CP1. And you can also, if you want to keep even more informations, you can remember phi and n. You can take the two vectors, a pair of two frames. So you are then taking value into the Stiefel manifold of two vectors, orthonormal two vectors in R4. And what is now interesting is that if you remember this transformation, which is the fifth direction, you see, so the two vectors corresponding to that are and so this is phi t and this is nt. So very quick, phi t is not going to be an immersion. But now if you do phi t wedge nt, you recover phi wedge n. That is, and this is, of course, you know, what Arnold is always insisting on in his papers, is that you should not work at the downstairs at the geometric level. You should go upstairs at the Lagrangian level. That is, okay, so what we have is that because things desingularize automatically. So the fifth direction is not seen anymore. And this is going to be, for us, very important. So, in fact, you have respectively Lagrangian and Legendrian structures on these two spaces. That is, again, so the Stiefel manifold is made of pairs of unit vectors which are orthogonal to each other. This is a wedge, so you have some kind of Hopf vibration from here to there by wedging. You just push by wedging the two vectors. And you have a contact form on V2R4, which is this form here. And what you see is that if you take this is a special Keller form here on this product. If you pull it back by the by the projection pi, this is a differential of your contact form. So you have this kind of very beautiful structure between the two spaces. Okay, and now if you go back to this object, so remember we are considering immersions of surfaces. So before going, so you have to observe, and this is important in the inside of the work I'm going to describe soon, is that they are respectively Keller-Einstein and Sazakian-Einstein. So Sazakian is an odd dimensional version of Keller. The cones issued from a five-dimensional Sazakian-Einstein manifolds is Keller. Okay, so now if you look at the Gauss maps which are here, so we have both phi wedge n and the pair phi n. So they are respectively, Legendrian. That is, you see your contact form is giving you are in 5 dimensions. V2R4 is diffeomorphic to S3 times S2. You have plane distributions which corresponds to the kernel of your contact form, and they are absolutely not integrable. Okay, because it's contact. And what you see is that your immersion, when you lift it up at the Legendrian level in 5 dimensions, it has to be everywhere tangent to your plane distributions. And moreover, if you go downstairs at phi wedge n, when you forget about phi n and you wedge them, you are becoming Lagrangian. So now, and of course, it is both are immersions. Huh? Both lambda and j are immersions. So now we are interested in studying Legendrian versus Lagrangian immersions. First of all, what you observe is that any C1 perturbation of a Gauss map within Lagrangian maps is still a Gauss map. And any Lagrangian immersion is locally plus or minus the Gauss map of a generalized immersion, which is called a Lie immersion. I'm not going to go into that, but I'm using it at some point. So this is due to Palmer. So in a sense, you see, here I was speaking about general constraints, general Legendrian and Lagrangian constraints. If I look at my Gauss maps here and there, they are fulfilling these constraints, and around them, everyone is also coming from a Gauss map. Okay, so now, what about the area? So this is known since a famous work of Lawson, that if phi is a minimal immersion, n is a branch minimal immersion, and phi wedge n is a minimal immersion as well. So he called them polar variety and bipolar surface. And now this is the area of the Gauss map. So this is the thing we are now considering. We're going to do a min-max with this object. So what is important to know also is that if you do min-max with this object and if you are constrained to be Lagrangian everywhere, you might say no way to be minimal because you have too many constraints. You see the space of authorized plane, the space of Lagrangian planes is three-dimensional. Okay, locally it's U2 quotiented by SO2. So, but nevertheless, if you allow for any perturbation which preserves the Lagrangian constraint, you become minimal. Of course, here I'm a bit enthusiastic. I say every perturbation which preserves the Lagrangian constraint. The one which preserve locally are called Hamiltonian, but here I'm speaking about all perturbations here. So in a sense, you see by looking, still having this Lagrangian constraint, it still gives still some hope to reach minimal surfaces at the Gauss map level. And now, there is another result by Castro and Urbano, which is telling you that if you know that you are a Gauss map, and if you know that it is minimal, then you can push your surface, you find locally a constant T, such that this object is a minimal immersion. So this is what is here. So it gives you some encouragement to study the variation of this area because you think that you are not too far. You have desingularized in a sense, your canonical family. You are not too far from studying minimal immersions in S3. Okay, so now we have to go into analysis because you have to see that, you know, if you do the area of J and you prescribe J star omega equals 0, this prescription is going to be variationally extremely challenging because it's not like what has been done with harmonic map. With harmonic map, you had a constraint, you had a pointwise constraint which was on G. Here, you have a pointwise constraint which is on the derivative of G. And this is, in a sense, very reminiscent to fluid mechanics. If you look at Arnold's formulation of Euler's equations, you see this constraint could be identified if you take a graph. This is simply, you are looking at incompressible maps, you see, and you are minimizing some energy among incompressible maps, if you want, or looking at critical points of, and this, you know, it's going to generate a very nasty object, which is called the pressure. Okay, in fluid mechanics. So this is really the object you have difficulty with. So here, this is also going to happen. In fact, the pressure is going to be the Lagrangian angle. You can see that if you are taking value, for instance, in C2, and omega is a classical, the canonical symplectic form, you see, if you pull back by J dz1 wedge dz2, you are going to have an object which is EI beta, so it's called the Lagrangian angle here, times the volume of J. When beta is constant, it means that you are calibrated, because here in C2 you are Galileo, so therefore it's you are nicely calibrated, your surface is nicely calibrated, but here beta is the pressure. Beta, for me, is the pressure. And this is an object on which you have no control at all. It is extremely bad. In fact, with my students, Filippo Gaia and Gérard Oriols, we construct a critical point of this one, which have infinite area everywhere, and which are nowhere continuous, so which are very, because you can play with this object if you have no control on the pressure. So this is very weird. So the first pioneered work in analysis on this variational problem is the famous paper of Sean and Wolfson. They were considering area minimizing Lagrangian maps. So what they proved, maybe it's a more restrictive framework, they proved it for more general symplectic manifold, but let's take it Keller-Einstein because the equation is nicer there. Every Lagrangian homology class is represented by an Hamiltonian stationary smooth branch immersion away from isolated conical singularities. So the Euler-Lagrange equation here is simply a Laplacian of beta equals 0, which you would think it's a nice equation. But there is an issue there, is that EI beta is well-defined, but beta is not well-defined. It's not unique valued. And in fact, what Sean and Wolfson discovered is that you can have minimizers in some, so there are examples by Mikhaïlev and Wolfson, in some spherical Lagrangian homology classes, which have these conical singularities like this. So these conical singularities, so they are of this form here. They described it, so they are all of that nature, where P and Q are integers. And they are stable if when P minus Q is plus or minus 1. So, and these conical singularities happen. And these are singularities around which beta is not univalued. And so this is really, it shows you that the problem is very challenging. So now the result I wanted to mention is a very recent result with, again, Alessandro Pighetti. So if you take a min-max family, no, we are looking not at minimizers, but min-max, where the width is strictly positive. No, we are looking at Legendrian immersions. So we are going up, so there are good reasons for that, which are made clear in the paper of Sean and Wolfson, is that there is no monotonicity formula downstairs, there is one upstairs at the Legendrian level. So if you look at the min-max here operation, which is non-trivial, then your width is realized by an Hamiltonian stationary branched immersion, which is smooth away from isolated conical singularities. The genus is controlled, and this is realized. So we achieved this, this min-max here in this way with isolated conical singularities, and we know we cannot do better. So this result is based on a result, on two results. So one I uploaded on arXiv last year, and another one which is on arXiv since May, the first part. And the second part is that we have written the proof, but it's going to be on arXiv soon. So it's a regularity result for critical points and not only for minimizers. So for critical points of the area where you have this, and you have to be in this class, but we reach this class easily. We have to be in this class of parametrized Hamiltonian stationary varifold. So now it's time to try to do the min-max operation for getting the Clifford torus. But I don't know if I have time to go into this. 5 minutes. So which min-max operation are we looking at? So we are taking, so here, this energy, which is the area I wrote before of the Gauss map, plus a null Lagrangian here. So this energy is less or equal than 4 times the Willmore energy. So equality holds if and only if the two principal curvatures are equal to each other. So therefore, and this is the case, for instance, for minimal surfaces. Or, no, I should say absolute value. Sorry. Yeah, absolute value. With Gérard Oriols, my student, we studied already the bottom, so what's happening at the lowest level. So we know it's 16 pi, and we know that it is achieved exactly if your Gauss map is of this form, x rotation of x. So we are in CP1 times CP1. So this rotation object is very important. This is going to be the crucial object for the min-max operation. So now, what's happening when you approach the ground state? So what we did is that, first of all, we proved that you can approach the ground state with any genus. So I'll show you an example. So sigma 2 is an arbitrary genus, and you can, with A, reach the 16 pi. I give you an example. You see, you have an S, so this is S3. So you push your surface using the Möbius group like that. You bring it to this plane here, R3. And there in R3, what you're going to have is a surface like this. So this is for genus 1. It is a tight surface. So tight surface means that the integral of k plus, the positive part of the Gauss map, is exactly equal to 4 pi. And so this is an example of what can happen is that you start with a nice surface, you push it in this way, and the surface is at the limit is like this. Then it is such an example. And here you can see on this example that you have two bubbles. You have to think, note that the Gauss map, phi is constant because phi is equal to the south pole, and little n is this map. And little n is covering exactly S2 once, you see, in a positive way, and once in a negative way. Then after you can have higher genus, and this will be something like this. But they are all tight surfaces. Okay? So what you observe is that in these examples, if you restrict to the positive part of the Gauss map, then you have only one bubble, one positive bubble. And this object is important. So this bubble, it gives you one rotation. So we call it the positive bubble. And you have G sigma 2 negative. Now, what is not ready yet, so I'm not claiming I have the Willmore conjecture right now at this stage using this approach, because this is in preparation. We have to show that this is the only way to approach the ground state. We are going to use the regularity theory with Pigatti that we are finishing. So, and now you have an important map that I call the polarization map, which is going to assign you the positive the rotation corresponding to the positive bubble. And you have to remember that all bubbles are of this form, where it's a constant rotation. So now the min-max is constructed out of this rotation. And I think I should be short in time, or yes. So what's going to happen is that if you have a non-zero genus surface, you are going to prove that the polarization map has degree from S3 into SO3 exactly 2 times the genus of the surface. And this is going to help you to produce a min-max theory. So just to say that this approach, you could imagine, so I'm not going into the min-max operation. Just one thing is that, where was the fifth direction? The fifth direction is there. There is a result by Castro and Urbano, which is telling you that the area, the index of the area, is exactly the index of the area of the Gauss map, plus 1. This is where your fifth direction is. And in particular, if you have an index 4, this is a Clifford torus, otherwise index 1. So, no, index 0 for the JDX. So what I mean is here is that you are going to have 4-dimensional min-max families. And so in higher codimension, what I suspect is that since now we don't have anymore this nasty direction, so it would be interesting to study an object which is called, so you are going to look again at Lagrangian Legendre level. Here, we are considering now immersions from S2 into Sn. And what is probably, I hope, is that to find a min-max problem of homological dimension n plus 1, which is based on the Hn of the isometry group of G2 Rn plus 1. Like here, you see this was the isometry group. This was, yeah, so these operations, you see, is part of the isometry group of G2R4. Okay? So, yeah, sorry for being a bit fast there. Thanks for your attention.
Okay, great. Thanks very much for the interesting talk. So let's start with some questions. Does anyone have any?
You say that you want to use a Gauss map to avoid surfaces.
Could you say it?
So you said that you want to use a Gauss map to avoid the surfaces becoming singular along the parallel family. But do you still have the fixed parameter? It seems you're using only the 4 parameters here.
You have the fifth parameter. You see, so if you work at this level, you don't see it because the wedge, because of what I wrote here. So it's not seen, and it is also confirmed by the result of Castro and Urbano that the index of the Clifford torus at this level, of the Gauss map of the Clifford torus is 4. So the fifth direction has disappeared. So you have smoothed out the min-max problem, the original min-max problem in that way.
Okay, thank you.
Any other questions?
Yeah.
Does the proof involve showing that the conical singularities are not there for
Yes.
min-max?
Yeah, that's important. But for Gauss maps, you see, beta is arctangent of kappa 1 plus arctangent of kappa 2. So you cannot realize Maslov classes. Yeah, of course, this is the main issue is to get rid of the conical singularities. So what is difficult is that in the min-max approach I'm doing, I could be at the boundary of the Gauss maps. That is, I could be, and this is what is not clarified yet. This is why I'm still very careful in not claiming that I have it yet, but I can be at the situation. So for an immersion, you have this strictly positive. You see, so it's a 4 vector taking value. So it's a 4 vector in R4. So and this is a Jacobian so it's like a number. Huh? So it's strictly positive. The problem is that in the min-max, I can reach this boundary, and I have to prove that this does not happen. So this is, I have good hope that I will be, that I'm really a Gauss map of a true immersion and not of a Lie immersion. So this, I don't know yet how to solve that part.
And And if there's no other questions, then let's thank the speaker again.
Thanks.